this is Guan, and I'm introducing KPerfIR towards an open and compiler-centric ecosystem for GPU kernel performance tooling on modern AI workloads. And this work was led by Meta and UC San Diego, and we also have collaborators from GMU and OpenAI. And so I will first introduce the background and our motivation, and then I will introduce our infrastructure for the performance tooling, which is called KPerfIR. And then we have a very nice example, which is a region-based timing tool. And finally, we will have some evaluations of the infrastructure. And as we all know, the modern AI workloads are very expensive. So improving their performance is to make money. And so this figure shows the trending of the cost to train an AI model. We can find it expanding year by year. So we have to do some GPU accelerations. And as a result, the price of NVIDIA is like booming. But the truth is GPU gain is getting harder and harder. And the reason is GPU hardwares are become specialized and asynchronous. So at the very first, GPU is a SIMD hardware. We only have the CUDA core. So the execution is parallel and sequential. And to accommodate the tensor computation, we then have the tensor core. And we can move the MMA computation into the tensor core. And to feed the tensor core, we then have the asynchronous data loading, which requires the pipeline design. So we will move the different workloads asynchronously, and we will design pipelines to orchestrate them between different hardwares. And as the story goes along, we then have the tensor memory accelerator, which is abbreviated as the TMA. So we can move the data loading into the dedicated TMA hardware. So we can have a more complex computation on the CUDA core. And this leads to a very hybrid and complex producer-consumer programming model. And to facilitate the development of this hybrid producer-consumer model, we have modern AI compilers to assist. So there are many AI compilers emerging in these recent years. For example, the TVM, the standard Keren. We also have Triton, we have JAX and MLIR things. And one feature of the modern AI compilers is they are modular and multi-level. That means for different operators and the different hardwares, we design a multi-layer IR to accommodate different high-level and low-level semantics. However, the hard truth is compiler design is very painful. The reason is we have no straightforward visibility to the IR structure. For example, we want to optimize the producer-consumer model shown in the middle. So we have to manipulate the IR. For example, we have the TT dot for the tensor core. We have the copy async for the TMA hardware. So if we want to do the WAP specialization, we have to insert the conditional node into the IR and branching to different executions. And on the other hand, we also have to design the pipeline design and insert correct barriers between different WAPs. And to optimize this, the programmer wants to profile the kernel they're written. For example, they use NCU. And now we only get some aggregated and coarse grained result from the profiler. For example, as shown here, this is the result from the official tool from NCU. And we only have some like coarse grained usage, throughput, and latency status. And similarly, we also have the torch profiler, which only tells you the latency of different kernels. So this is not enough to optimize a compiler fine-grained design. So the developer may have a harsh time to improve all these fine-grained details. So the idea is how to provide a general and extensive support for performance profiling in modern AI compilers. So our insight is, compared to prior profiler arts where profiler and compiler are isolated, why not just make them together? That means you put the profiler into the compiler. So the solution is very elegant. Is in the existing compiler infrastructure, we can insert some new dialects with operations and passes, and we can use them to build third-party performance tools, which contain some analysis passes. And we can utilize this infrastructure to build different execution tools and get the traces and find performance insights from them. So with this infrastructure, we can put the semantic from the IR into the profiling infrastructure to get some programmable performance tools. And we can also feedback the profiling result to the compiler to get some profiling-driven compiler passes. And finally, because we are delivering a universal infrastructure, we can build different and reusable tools, which is the third-party performance tools. So how do we design this infrastructure? So here I show the general Triton IR structure, which has the user program, the Triton dialects, and the low-level LLVM dialect. And the first things we do is to develop a multi-layer IR to implement the semantic for profiling, which is known as the KPerfIR. It has the record OP, which represent the recording, and we have some low-level operators accordingly. And the second part is we will have an instrumentation pass, and this will instrument the IR of the record OP into the correct position in the user's program. And finally, to manage the profiling result, we will have to implement a runtime for the tool, which deals with the profile data readback and the decoding of the profiling result. And for the detailed implementation, there are 3 features. So the first one is we have a universal interface. That is the record OP, which has 4 different features, which have 4 different metrics. That is the region ID, the tag, the metrics, and the granularity. So the user can build different tools on top of this universal interface. And the second one is we have a multi-layer IR design, which corresponds to different layer of the IR. And the third part is we have And the third part is we have a cross-platform code generation, which lower the IR layer by layer to different hardwares, so we can have the universal interface, even on different hardwares. So you can find details in our code and our paper. And next, I will introduce a very elegant example. It's called region-based timing tool implement with the infrastructure. And so sometimes we want to optimize the fine-grained orchestration design as introduced in the motivation part. So this can be very challenging. And for example, we have a flash attention kernel. It will have many low-level orchestration. And we want to implement a 3-stage orchestration design, which is shown in this part. So what if we can have a very beautiful trace that reflect the execution of the current kernel, so we can tweak the IR and get the feedback and improve the performance. So to implement this tool, we have to use the 3 different components as introduced before. So for the multi-layer IR, we can implement the tool records for the region-based performance tool, which is to get the time tick-tocks in the program and store it in the memory. And for the second part is we can have the instrumentation passes to insert the records into the right places. So we have 2 different interfaces. The first one is the user interface, where the end user can insert the IRs directly. And the second part is the compiler interface, which is compiler passes that instrument the IRs automatically. So for the third part, we have to implement the runtime, which result in the runtime memory management and some post-processing to process the result afterwards. So with this tool, we can get a very beautiful trace of the intra-kernel tracing. So on the top is a vanilla FA3 kernel, and at the bottom is an improved one, given the insights from the previous one. So the first thing is we can identify the critical path of the current execution. For example, we can parse the producer-consumer's dependencies and find out which is the bottleneck and where is the bubbles. And in this example, we find that this particular barrier is the bubble, and we can move it forward. So there will be less execution bubbles in the trace, so the performance can be improved. And the final part is the evaluation. So how to evaluate such an infrastructure? So as I introduced, there will be 3 features. So the first one is we provide a programmable performance tool with IRs. And the second part is some profiling-driven compiler passes. And the third part is a reusable and portable tool. So to evaluate the first part, given the performance insights, we optimize the F3 kernel, which outperforms its vanilla version in Triton and also the version in CUDA. So the blue bars shows the implementation in CUDA, and the purple bars shows the vanilla Triton version. So we can find that the vanilla one actually cannot compete with the CUDA one. So with the tools assistant, we can remove the bubbles in the trace, and the performance is improved, and it can now outperforms the one in the CUDA. And so the second part is we can give this profiling insights, and we can build a cost model to guide the optimization of the producer-consumer model. So the idea is we profile different regions, and we build an analytic model to execute different parts, and we can calculate the overall efficiency given the current execution. So this can be used as a compiler pass to optimize the F3 kernel automatically. So for the third part, we want to evaluate the portability. So here we evaluate the performance tool on different backends and with reference to its latency and the memory. So on the left side, it shows the latency overhead. We can find that it is less than 10% for most of the production level kernels. That is the SOTA gem kernels and the flash attention kernels. And we can also guarantee the result to be accurate with some post-processing, which we call trace replay. And on the right side is the evaluation of the memory overhead. We can find that with even not so much shared memory left for the profiling tool, we can get the accurate result, and which is adaptive to support the optimization to provide an accurate trace. And finally, some takeaways. And in this work, we first provide performance and tool infrastructure called KPerfIR, and it is built upon the Triton compiler. And the second part is we build an intra-kernel performance tool, which can be used to tracing the async execution and to help the optimization. And we envision this can build an ecosystem, which is a community with composable and reusable tools to be shared by different users and to facilitate even high-level ideas. And finally, is some acknowledgement. We would like to thank our team from Meta, and this work was inspired by some work from the Mosaic GPU. And thank you. Here is a QR code where you can find our source code. Thank you.